But yeah, so I've given myself the very challenging task of trying to teach you the Einstein Toolkit in a short amount of time. And I'm not officially part of the cohort of maintainers, so that's why there's this disclaimer. Views are on my own. I'm going to tell you about my approach to the Einstein Toolkit. Someone else might give their different approach. But yeah, my name is Ms. Gabriele. I'm a finishing PhD student at the University of Arizona. I've used the Einstein Toolkit for 6 years at this point, and I consider myself knowledgeable enough to tell you about it. And I would like to start with a few public service announcements. First is that I'm here today and tomorrow in this 4809 beautiful office in the fourth floor. And I will absolutely love if you stop by and chat with me. I know many of you have worked on E&M stuff, and that's what you're going to hear more today at my seminar. I want to learn what you're doing, and please stop by, chat about anything, about what you like about Lisbon, what's your favorite type of cacti, whatever. I absolutely would love to chat with you. So please stop by. So this is my first one. Second is, as we're going to see, you are probably going to need a little bit more help or a little bit more support than what I can tell you in 1 hour. I'm very, very, very happy to be able to help you. So there's a few ways you can get in touch with me. So that's my email address. There's a Telegram group that I use mostly for packaging the Einstein Toolkit called Pivots. And then there's me. So you can send me an email, you can reach out on Telegram, or if I'm around, if you ever cross your path with me at conference, whatever, I'm always available to chat with you. And again, today and tomorrow, if you want to explore more of what I'm going to talk today, I'm very happy to spend as much time as you need. So if you find me, I will always be thrilled to talk to you. And as a final service announcement is, well, it's okay to be lost. This Einstein Toolkit is difficult. Einstein Toolkit requires thousands of person hours to be built. It's impossible to understand it in 1 hour. It's impossible to understand it in 2, 5, 10 hours. It's absolutely okay to not follow or not be able to understand what's going on because it's complex. There's so many moving parts. There's so much that goes into the Einstein Toolkit. And that's why also this talk is recorded. So what I decided to do is I'm going to focus on understanding of some key elements within the Einstein Toolkit. I don't think you'll be able to follow along. Actually, I'm going to take some shortcuts so you won't be able to follow along because I'm going to skip compilation. I'm going to skip running some stuff. But everything is recorded so that you can review it. You can follow at your own pace. You can see what's going on and try to do in your own time. So it's okay to be lost. It's okay to not understand. Just try to get as much as you can. And at any time, feel absolutely free to interject, to ask questions, to make comments. It's perfectly acceptable, actually, it's encouraged. Okay, so with that, I would like to give you like a chart, a map of what the Einstein Toolkit is and what the Einstein Toolkit is not. And this is once again is going to underline how Einstein Toolkit is fundamentally a complex piece of software. So this is a very busy plot like a graphics that I tried making yesterday to illustrate the Einstein Toolkit cactus ecosystem. So let me try to navigate you in this very complex world of numerical activity or relativistic astrophysics simulations with open source codes. So we have this big red circle, or well, ellipses. This is the Einstein Toolkit. So the Einstein Toolkit is an open source, community-driven project for numerical relativity in relativistic astrophysics. Einstein Toolkit has many components. The probably most important component is Cactus. So Cactus is a computational framework. It was developed in the 90s. Being a computational framework means that essentially it's a collection of libraries that people can use to build more complex stuff. For instance, when you use Cactus, you don't have to worry about MPI or message passaging. You don't have to worry about parallelization. You don't have to worry about build system. You don't have to worry about linking. A lot of like technical details that go into developing complex piece of high performance computing codes are taken care for you. So with this Cactus, what we have here is a foundation upon which we can build numerical relativity codes. And in the language of Cactus, the modules that implement physics are called thorns. Now, thorns, this is a misnomer. Technically, cacti have spines, not thorns, but we haven't heard of any botanists complaining about that. So for the past 20 years, we've been calling them thorns. So thorns implement physics, as well as memory management, as well as grid structure, as well as checkpointing, as well as essentially all the non-trivial, if you want, again, build system, parallelization, all the non-trivial stuff is in thorns. So many thorns are within the Einstein Toolkit. So as we can see here, there's this lime circle is what are thorns. So components that extend the features or implement feature, many are part of the Einstein Toolkit. So there's an overlap, but there's many that are not part of the Einstein Toolkit. For instance, here we have this Spritz code, which is a GMHD code. There is a thorn, works with Cactus. It's very well compatible with the Einstein Toolkit, but it's not part of the Einstein Toolkit. You can download it, it's open source, but when you download the Einstein Toolkit, you're not going to find Spritz. And there's also many thorns, which are private source. People do not share those thorns with other people. So for instance, you yourself, you can develop your thorn for your project, for your group, and keep it for yourself. That's perfectly fine. There's no problem with that. If later down the road you want to share it, that's great, but you don't have to do it. So this is the core of the Einstein Toolkit. It's Cactus infrastructure, as well as a series of thorns that enable science. So we have a bunch of GMHD solvers, we have a bunch of space-time solvers, we have all sorts of stuff. Roca solvers, we have a scalar field, everything is in 3D for the most part. Then with the Einstein Toolkit, there's also a series of utilities. So that we can see here. Once again, part of them are part of the Einstein Toolkit, but not all of them. There is utilities which are not officially part of the Einstein Toolkit, but they work very well with the Einstein Toolkit. For instance, here I have this NeRPy, which is not officially part of the Einstein Toolkit, but is essentially designed to be to work along with the Einstein Toolkit. There is utilities for post-processing, there's utilities for pre-processing, there's utilities for downloading the Einstein Toolkit, for running simulations, there's a lot. Many of them are part of the Einstein Toolkit, many of them are not part of the Einstein Toolkit. Then we also have codes that have nothing to do with Cactus. There's at least one code, it's called Cellforce 1D. There is a Cellforce code that is not part of the Einstein Toolkit. Sorry, that is part of the Einstein Toolkit, but it's not based on Cactus. So when you download the Einstein Toolkit, you can optionally also download this code. And of course, there's an entire universe of codes that are not part of the Einstein Toolkit. Your own code is most likely not part of the Einstein Toolkit. Some of these codes do talk quite well with the Einstein Toolkit. For instance, if you want to do binding to some mergers, maybe you're going to use the Lorraine code. Now, this is my rendition of the Louvre pyramid in Paris. I know Lorraine is developed in Paris. So Lorraine is not part of the Einstein Toolkit, but there's a bridge so that you can so it's very easy to integrate Lorraine simulations with Lorraine initial data with Einstein Toolkit simulations. And this is true for many codes, because they're developed separately, but there's some form of like reader or bridge so that you can interface with those codes. This is typically the case for initial data codes, for instance, or for external libraries, say for linear algebra. We're not developing LAPAC or BLAS, if you know what I'm talking about. And finally, I always like to emphasize that when we're considering projects of this size, again, there's like hundreds of thousands of lines of codes, hundreds of thousands, well, thousands for sure of person hours of work. There's a lot of infrastructure. Infrastructure means continuous integration, documentation, how to ensure that this keeps working. And this, I think it's important to emphasize. It's not just code. There's all this infrastructure that allows us to keep working with this code, to keep it running, and to keep being able to download it, being able to use it. So there's people that spend time just on this, and this is very valuable. So I consider this part of the Einstein Toolkit project. So this is, if you want, the Einstein Toolkit Cactus ecosystem. There's a lot of very useful codes that are part of the Einstein Toolkit, Not all of them are cactus. There's very useful codes that are not part of the Einstein Toolkit, but they are cactus. So as you can see, it's probably unlikely that you can just download everything with, I don't know, git clone, because there's so much to it. So that's why we're going to start the tutorial today with downloading and compiling the Einstein Toolkit. And what I'm going to do next, I'm going to show you how to run a simulation, and then I'm going to show you how to make quick plots for the simulation. And maybe there's a good point to take any question, if there is any. Okay, I don't see any question. So I'm going to, I think I don't have anything else. Yes. So I'm going to switch to the Einstein Toolkit website. This is the website. And what we care about here for the first step is downloading. There's a big download button. And if we click that, what we're going to see is a series of instructions. Now, here, the very first instruction is to download one of those utilities that I mentioned. As I said, part of the Einstein Toolkit, we have a series of useful codes that are not cactus. And this piece of code is get components. Now, Einstein Toolkit uses a model in which we have releases. Every 6 months, typically in May and November, there's a new version of the Einstein Toolkit. Typically, the versions are very similar. So the version that you downloaded in May is going to be very similar to the version that you download in November, with a section of maybe new thorns or new features. So most often when you start new projects, you can just download a version and keep using for years. You don't necessarily have to update. So in this first line here, what we do is we download on our computer the get components code. So now I'm going to do it. I'm going to paste this line and get the get component file. Now we can have a look for mostly to, because you're curious to see what's this get component. Now, get component is a complex Perl script. What it does is solves the problem fetching all the other codes that I've mentioned. Many codes are on GitHub, others are on Bitbucket, others are with SVN on private servers. So get components solves the problem fetching all these codes and putting it in a single place. So we can make get component executable. And then the next step here is to download the Einstein Toolkit. So now, if we paste this line here, now I already have it, so I'm going to say no. I don't care about this. So what we get is a thorn list. So Einstein Toolkit.th is a thorn list. As mentioned again, thorns are the components that include the physics and the computation behind the Einstein Toolkit. And the thorn list is just a collection of thorns. So as we can see, the structure of a thorn list is a series of, if you want, stanzas, where I define where I should find this code, what branch, if it's Git, and the names of the various modules that I find inside the thorn. So essentially what this thorn list is describes what's inside the Einstein Toolkit. So we can go to have a look at this repo, or whatever. Actually, no, sorry about that. Let's have a look at this repo. Okay, it doesn't work, whatever. It's not important. So here what we have is, again, a collection of where to find these thorns, and get components knows how to parse all this stuff and will fetch all the components for you. So if we scroll at the bottom, there's also a section for you. If you have your own thorns, you can just add a bunch of lines here so that for your group, you can have your own thorns, and get components will know how to download those thorns for you. So this is one way to ensure that the Einstein Toolkit can be extended. It can be extended the way you want it. So here, if you're curious, you can have a look at all these different thorns that we have here. So here we have a pit null code that is for Cauchy characteristic extraction. We have Mathlachlan, which is a space-time solver, where we have the BSSN and CCZ4 formalisms. We have Llama, that is for multi-patch. We have Lean, which is another space-time solver. We have something for finite differencing. We have Lorem that I already mentioned. We have all these external libraries, which are numerical libraries for the Einstein Toolkit. We have a bunch of utilities again, and some initial data. So this is what's inside the Einstein Toolkit. Once you downloaded that, what you're going to find is you're going to end up with a Cactus folder. Now, the Cactus folder, by the way, is the font size large enough? Should I increase the font size? Can you? Okay, no one. A bit larger. Okay. So get components will probably take a couple of minutes. Once you download all the files, you're going to find this. This is the Cactus folder. We often refer to it as the Cactus source there. There's a lot of stuff in here. Most of it is probably not going to be particularly important for you. It's there because it's needed for the system, but you're not really going to work with it too much. But I'm going to draw your attention to some details. For instance, the arrangements folder contains all those top level collection of thorns that I mentioned before. So for instance, there we have a rock arrangement that contains a series of thorns that are for evolving broken fields. We have I don't know, like a carpet arrangement that is for adaptive mesh refinement. We have once again, we have a llama that is for multi-batch and so on. If we look at the repos folder, this is exactly what Get components uploaded. If you remember, we have all this, most of them are Git repos, some are SVN repos. So here are the single repositories in the sense of like computer science, so a collection of, again, Git or SVN repositories, which we have all the different modules. So that's where Get components will download the files. Then we have some example par file, and I'm going to touch upon par file in a second. So there's a par folder, which there is a GW protein. There's a TOV example that I'm going to talk about more later. And what else do we have here? I'm going to talk about the scene factory in a second. And then we have a source folder, which contains Cactus. And that's pretty much it, I think. So the way, so just again to emphasize what we've done so far, we got Get components, which is one of these modules in the Einstein Toolkit, and we use Get components to download everything else, almost everything else. Now we're going to use a second very useful utility in the Einstein Toolkit called SimFactory. Now, SimFactory is a big piece of software. SimFactory lives within the SimFactory folder and is a Python module that does a lot of stuff. So here we can see all the options. You can see all the commands that we can run. There's so many. But most importantly, we're going to use SimFactory for compiling the Einstein Toolkit. We're going to use SimFactory for submitting simulations and running simulations. And we're going to use SimFactory because SimFactory knows about a lot of supercomputers. So let's start from that. So let's start from the machine database. Now, once again, as mentioned, Einstein Toolkit is a complex piece of software. It's not trivial to compile. Especially, it's not trivial to compile if you want to take the most out of it. If you have like national supercomputers, and there's a very specific tuning of parameters that you have to do, there's specific choices of, say, how to split processes versus threads, all this stuff. It is difficult. Compiling the Einstein Toolkit, I spent days of my life compiling the Einstein Toolkit. But this is not an effort that has to be duplicated. If I do it for one supercomputer, I can just tell you how to do it. So as part of the Einstein Toolkit project, we also collect what we call configuration files, essentially. So in the machine database, which I'm going to show you in a second, so here we have a SimFactory. We have this MDB. So this is machine database, which lives inside the SimFactory. What we have is first a series of machines. So this is a list of supercomputers. Maybe you recognize some names. For instance, Frontera is a supercomputer that I personally worked on. And here we have a series of essentially configurations. So, for instance, how many nodes we have, how many cores, what's maximum hold time, a lot of very useful information that Sympactory will be able to read and act upon so that you don't have to. So that if you ever have to run on Frontier, someone, in this case, it's me, has already put a lot of effort for you so that you can just run. And this is amazing. When you find a computer that's already supported, it means that you don't have to spend days fighting against the system. So as part of the machine database, there's 4 files, which I mentioned because most likely, if you're going to compile the Einstein Toolkit on your computer or on your local cluster, well, probably you're not going to have it as part of these. So you probably will have to fiddle around with this yourself. So I'm going to spend a few minutes talking about that. So there's 4 main files. The first one is the .ini file. The .ini file describes the properties of the system, essentially, of the queues. It describes what modules you need or you don't need to compile and to use the Einstein Toolkit. There's also a regular expression here, which is, let's say it's optional, but it's mostly used so that Sympactory automatically identifies what machine is on, which is very nice. So this is the ini file. Second, we have Second, we have the option list. So let's look at Frontier once again. Now, this is the more tricky file. In the option list, we specify how to compile this code. So what executable we use for like C compiler, Fortran compiler, what flags we use. And now this looks extremely intimidating, and I'm going to tell you a couple of secrets in a second. All these flags, a bunch of other stuff that seems pulled out of I don't know where. So this is a collection of build options that Einstein Toolkit is going to use to compile essentially Cactus and all these forms. And so this is for Frontier. The next one that we have, so we had option list. Next, we have run scripts. These are typically relatively simple, well, comparatively speaking. So this is how you're going to run on your cluster. Maybe I should say, I'm giving a lot for granted, but Einstein Toolkit typically requires supercomputers. You're going to typically run on hundreds of cores. You're not going to run on your computer for any production simulation. So you have to go through queue system, scheduling system, and you have to use the proper submission files and run files. So here, what I'm doing is I'm using this ID run, which is the program that the Texas Advanced Center for Computing tell me I should use when I want to run on their cluster. So to build this, you're going to use information provided by your system administrator for in most cases. And most of it is actually not needed, is for performance tuning. So, and again, I'm going to spill my secrets and open secrets in 1 minute on how to actually do this, which seems like, I don't know, Egyptian, but it's a little bit easier than that. And finally, we have the submit scripts. So the submit script is what you will have. So this line is pretty much the same. It's always the same. It's blah, blah, blah. But the top section is what you will use to control your submission on the job scheduler. So again, I'm assuming that you're familiar with running supercomputers. If you're not, I can provide a little bit more background on clusters and what I mean with this. So these are the 4 files that you need when you want to run the Einstein Toolkit or Cactus-based codes using Sympactory on supercomputers. But now, if you the secrets, again, maybe I should not call them secrets, they're not secrets. But the trick is, there's 2 tricks. One, there's a generic file, there's a generic configuration that you can use that is going to be good enough to begin with, at least for your computer. So if you want to start exploring the Einstein Toolkit, you can use the generic configuration, which let's say generic. So here, for instance, there's something that is here for you. So this is going to work on most computers. It's not going to be the best one. It's not going to be what you want to use for production runs on supercomputers. But if you start exploring the Einstein Toolkit on your computer, on our workstation, you can just use the generic configuration. So this is for here for you. We can also look at the option list of MDB. There's a generic. So it uses very standard G Fortran, GCC, G++, very standard codes that you are going to have on your Linux system out of the box, most likely. So if you want to start using the Einstein Toolkit on your computer, well, then there's an initial step in which you configure SimFactory to essentially use this generic configuration. I don't remember how to do it. I think it's something like SimFactory setup, and it asks a bunch of questions, and then you just put the answer the questions, which are like username, whatever, and then I think automatically this is going to use a generic configuration. So like, let's see, whatever. I don't want that. Okay, save content, yes. So what happened here is SimFactory wrote a file, the dev.local.ini with this information, and I think from here you can move to compiling. Okay, so this is one. So if you want to start using the Einstein Toolkit, you can just use the generic configuration. And two, most supercomputers look alike in the sense that, for instance, I'm thinking about the Texas Advanced Center for Computing. Texas Advanced Center for Computing, they have many supercomputers, and every few years they buy a new supercomputer. But the next supercomputer is just going to be a small improvement upon the previous one, or like a small variation. And on most famous supercomputers, we already have the configuration in the Einstein Toolkit. So you can just copy the previous one, change a little bit the modules, change a little bit the directory structure, and you're going to have the next one. So the way I typically approach compiling the Einstein Toolkit on a new supercomputer is this. I go into the SimFactory MDB option list file. Now, this is where all the configurations are. Now, suppose I am on an Intel supercomputer, then I know the Intel compiler is called ICC. So what I do is I grab ICC in here, and here I can find all the configuration files that already use ICC as compiler. And I'm going to open one and find something that is similar to what I'm compiling. So essentially, most of the time, what you do is you just start from something that already exists, and you adjust the paths to it. And sometimes you have to ask for the system administrators for a little bit of help, but often you don't. So the MDB is a very, very rich repository of configuration files that you can immediately use for compiling on your supercomputer. Questions? When I don't get any questions, I don't know if it's because nothing is clear or it's because you already know everything that I'm talking about. So any feedback here would be.
Is the code that heavy that you certainly need to use a supercomputer, or can you also use a local?
Yes. So it depends. Oh yeah, thanks. Is the code so heavy that you need to use a supercomputer? The question is, and the answer is, so on your laptop, most likely, so this type of code is most likely bound by memory. So these are 3D simulations. So if you want to run binary files, or black holes, you need a lot of memory. Your laptop probably has around 32 gigabytes of memory. This is not going to fit any important, any simulations with enough resolution to be useful. So what most people do is they prototype on their computer. They run small simulations. They check that things are working on their computer. And then when they know what they're doing, they move to the supercomputer. Sometimes if you have very simple simulations or very, 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 very short simulation, then you can fit on your local computer. But I would say that the traditional use case is to run on supercomputers. Okay, so any more questions?
So if we already have like a checked out version of the Einstein Toolkit, how can we update to the newest version?
Yes. So the question is, if we already have a version of the Einstein Toolkit, how can I update to the next version? Now I'm going to give you two answers: what I do and what probably is the recommended way to do it. What I do is I just create a new folder and check out a new version. This is because I don't want things to be messed up, and also because I typically, as a developer, I typically modify thorns, so there's my stuff embedded in the normal Einstein toolkit. So this will clash with the normal update procedure. So I typically what I do is I move Cactus to, as you see, Cactus 2019 apparently, and I check out a new version. I think get components is able to, when you run it, I think it asks you, do you want to update all your components? So what it does, it goes inside each. If you have the new Einstein Toolkit.ph, so instead of 22, the next one is going to be 2305. If you have the new one, you should be able to go through this, and get components is going to go inside each repository, and I'm going to update to this branch. I would not necessarily recommend doing that, mostly because unless you're starting a new set of simulations, I would recommend sticking with one version of Einstein Toolkit for a set of simulations, so that you don't introduce any weird feature stuff. Okay, so now that we've talked about SimFactory, we can move on actually building SimFactory, building Einstein Toolkit. And for this, once again we're going to use SimFactory. So the command is quite simple. Is SimFactory bin sim. Oh, sorry, would be in the Cactus, SimFactory bin sim, and then build. Now, build takes a lot of flags, optional flag. Let's see if I can help. Let's have a look at the flags that build can take. What we can provide is we can provide a form list, we can provide a specific option list, and we can provide a lot of stuff. So the form list that you download is a form list with all the components that are within the Einstein Toolkit. But when you're running a simulation, you're not going to use, I don't know, most likely, you're not going to use CL, I don't know, like OpenCL. Like here, there's a bunch of codes for like example. Like you're not going to use WaveToy 1D F77 in your simulations. This is an example that is part of the Einstein Toolkit for you to see how to use it. By the way, Einstein Toolkit is a C, C++, Fortran code, Python code, Mathematica code, Perl, Bash. Okay, there's a lot of stuff in it. So there's many forms that are objectively useless. Like you will never use them. Unless, no, you'll never use it. Like with only 1D F77, you're never going to use it. But if you just compile this form list, this is going to take, you're going to compile codes that you don't need. This is going to take time. This is going to make your executable larger for no good reason. Every time you have to recompile, it's going to be more expensive. So what the Einstein Toolkit supports is compiling smaller versions of this form list with all of the forms that you use. So this is going to be much faster, much leaner, and much better. And you can do this, you can have multiple what we call configurations. So configuration is essentially a set of choices on how to compile the Einstein Toolkit. This most typically means different form lists. For instance, you have simulations with binary submergers, where you need all the geometry codes. Then you have simulations with a scalar field, which you don't need anything of the geometry codes. You just need your scalar field evolution code. So you can have a configuration that is for the binary submerger. You can have a configuration that is for the scalar field evolution. So when you compile, you can specify a configuration, which is the name that you choose and you give. It's a mnemonic name completely of your choosing that is going to tell you, okay, this is going to be for geometry, this is going to be for scalar field, or this is going to be my first version of the code, this is going to be my second version. So configurations are essentially, again, set of choices that you pick for how you want to compile the Einstein Toolkit, with which codes, how, and so on. So when we compile the Einstein Toolkit, the base command is build. Next, we're going to provide what configuration we want to use. I'm going to specify the flags here. I think you can just put the name. And here, you can put whatever name you want. For instance, typically when I'm compiling a new supercomputer, I have a configuration called complete, where I compile the entirety of the Einstein Toolkit so that I can run tests. Because the Einstein Toolkit comes with unit tests to check, things are right. So my first step typically is to compile a complete Einstein toolkit. This is can take up to 2 hours, depending on how many cores you have. And then we can provide a thorn list where, for instance, if we want to compile the entirety, it's going to be the Einstein Toolkit.th that we got at the beginning. Now, I'm not going to do this now on my computer because it will take forever and wouldn't provide anything useful. But instead, I want to tell you of a very, 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 very useful utility, which is part of the Einstein Toolkit, and it's called make thorn lists. But to discuss that, I have to first introduce you to the idea of par files. So we discuss thorn lists, which are the collection of modules that are going to be compiled with Cactus. And then all these modules are there. And when you run a simulation, running a simulation in the Einstein Toolkit means writing a parameter file in which you specify how you want to control all these forms. For instance, say there's a form for binary black hole mergers, and you want to set up the initial data for binary black holes. A parameter could be the mass of the black holes, or the initial momentum, or the spin, or the resolution. These are all parameters that end up in files called parameter files, like this static TOV file, in which we choose which forms we want to activate. And again, you can compile everything, but only use a subset of the forms. Of course, you have to, if you want to use a form, you have to have compiled it. So here we specify which forms we want to use, and we set all these parameters. There's a gazillion parameters. So for instance, let's have a look at parameter, something that's physical and we can understand. The TOV solver parameter. So this is a single neutron star. So it's a TOV, total amount of panavium bulk of type of initial data. And so we say, okay, in the TOV solver form, we want to set the parameter TOV rho central to this value, and to set the parameter TOV gamma to TOV k to 100. So in this way, we're controlling the physics. We compiled once with the Einstein Toolkit with TOV solver inside, and now we can run any simulation we want for TOV stars. We just have to tweak these parameters. And there's lots of parameters. One of the critical points in using the Einstein Toolkit is messing around with these par files. So for instance, here we have what output we want. So we want the density, the pressure, internal energy, specific internal energy, velocity, every 256 iterations, and so on. There's a bunch of parameters like this, which I don't have time to discuss, unfortunately. So in this star file, we have only a subset of all the thorns. We don't need thorns for binary black holes here as a TOV star. So what I would recommend doing is producing a thorn list that is specific for the problem you want to solve. Once again, because this will make everything much leaner, and especially when you do development, it's very useful to be able to recompile quickly. And this is quite easy to do. There's a utility called, so if we go inside utils, I think it's called make, or utils, let's see, scripts. There's a make thorn list utility. Now it takes 2 parameters. One is, I think it's called -m, which is the master thorn list, which is always going to be thorn list Einstein Toolkit, and then a parameter file, like this static TOV par. So now when I run this, what happens is that the script is going to look at my par file. It's going to find all the thorns that are needed, all the thorns that that are required for my simulation, and it's going to produce a new thorn list that only contains the thorns that are needed for the simulation. So now I can save this in thorn list static tov.th, for instance. So now I have a new thorn list, which is a reduced version. I think, again, this is so useful. And okay, so now we can go back to compiling. So we have our sim build, we have our configuration. We had what was the name? We can call it static TOV. And now we can provide a thorn list, our static TOV.th. Now I can try running this. It will probably fail. Okay, well, this is now compiling. I'm going to kill it because I'm recording. My computer is probably going to explode otherwise. But maybe if things work for you, you should be able to maybe compile. I don't know. If not, we can discuss it later. So at the end of this, once the compilation is completed, okay, we're going to be at the point in which we can run simulations. So what you're going to find is you're going to have a folder called so two folders. One is in configs, which is all the configurations I've mentioned. So let's see what I have in my configs folder. I have, well, sim is the default name of the configuration. And then there should be an exe folder, I think, which maybe I don't have because I didn't complete the compilation. But the exe folder is going to contain an executable.
Can you go back to the command?
Yes. So I think it's build. I think I put the name of the configuration here and thorn this. But you had to do the setup in order for this to work.
Yeah.
Okay, I think this is it. But again, we can look at that together. I'm trying to give you some sense of what are the steps. Yes. So what I'm doing here is I'm calling the script make thorn list. I'm providing a list with all the thorns that I have, and I'm providing the part file that I want to simulate. And the output is typed into a new thorn list. Okay. So if you have problems, we can look at that together. Okay, now we've compiled the thorn list. We have a new executable that we can use to run our simulations. Now, again, I'm going to assume that you're running on a supercomputer, and I'm going to assume that you set up all the submit script and all this stuff, because in my experience, that's what you're going to do most often. And when you have a supercomputer, what you have is you have a scheduling system. You have a job scheduler. You have to wait your turn before you can run something. And SimFactory knows about this, so it can interact with the scheduling system. So if you want to run a simulation, what you can do is you can once again use SimFactory. Instead of using the build command, we're going to use the command submit. So this is going to, if you configure properly your system, this is going to submit to the job scheduler. Then we provide a name for the simulation. Again, this is a mnemonic name for us to know what we're simulating. In this case, is 2V 128. 128 is the central energy density. And then we provide the part file, which is going to be inside R and static 2V. We're going to provide the configuration, which I think we call static 2V. This is not the end of the story. When we submit, we have to ask how many resources we want to use. So for instance, we have to ask how many cores, how much time, all this stuff. Once again, if you're on a supported supercomputer, or if you configure your computer correctly, the system will know how the different nodes look like, how many cores each node is going to have. So what you can just do, you can specify how many cores in total you want to use. And you do this with the processes flag. So suppose each node has 64 cores, you want to use 2 nodes, then you're going to specify 128. So the system will know how to split everything for you, so you don't have to. So this is going to tell, okay, I want to submit this with 128 cores, and the next piece of information is required on most supercomputers is the so-called wall time. So the wall time is for how long you want a simulation to run. Let's say 12 hours. Now, this concept of wall time is important. Simulations can take a very long time, like months, to complete. And supercomputers do not allow you to run one simulation for a month. That's so long. Most supercomputers do not allow you to run a simulation for 1 day. At most, it's 12 hours. So Einstein Toolkit supports checkpointing, which means that here I'm asking for 12 hours. 11 hours and 30 of running time, Einstein Toolkit is going to save its state to disk so that I can submit a new run where the new run is going to start from the previous one. So I can have multiple checkpoints or restarts in which I fill my month-long simulation in multiple small pieces of 12 hours at a time. This is a very critical feature that is necessary to run on supercomputers. So this is set by your administrators. You cannot do anything about. I mean, you can choose you cannot go above the limit set by your system admins. You always have to be below. And the whole time is not tied in any ways to how much your simulation, well, in most ways, in how much you think your simulation is going to take. If your simulation is going to take 1 hour, even if you ask for longer, it's not a big deal. If your simulation is going to last for 20 hours, well, at 12 hours, you're going to have the first checkpoint, and then you're going to submit a new one, and you're going to continue the simulation where it stopped. So this particular simulation, static QV, should take an hour or so. So once again, I'm not going to run it because we don't have an hour, and my computer has only 2 cores, so it will die. But if you submit a simulation, you wait in the queue, the simulation runs. At the end, you're going to have you're going to have a, I call it TOV star. You're going to have a TOV star result folder. So let's have a look at this folder. And in this folder, what we have, so now TOV star is the name I should have chosen, but I chose the wrong name for my simulation. So this, I call it TOV 128. When I ran this, I call it TOV star. So this is the name that you chose for your simulation. So suppose you're running 10 simulations, you're going to have 10 folders with 10 simulation names that you chose. For instance, you explore and 10 different Newton stuff. Inside this folder, you're going to have a checkpoints folder. Checkpoints, which in my case is empty, because I think, yeah, because the simulation is full, I can finish without making checkpoints. It's going to contain a bunch of files, binary files that you will never open yourself, that contain the state of the simulation at a point in which the simulation had to stop because of wall time. So this contains all the gate functions, all the variables that are needed to compute the next iteration. Then there's going to be this output. You're going to have a series of output, 000, 0001, 0002. These are all the different restarts. So when in 0000 is our first run. Then if the simulation has to continue, we submit again, we're going to have a 0001 and so on. So you're going to have many of these folders which contain the results for that chunk of simulation. And then there's some extra stuff that is not particularly important, so I'm not going to discuss. We can look inside our folder here, inside the static QV. So we have 3 important files. One is the tar file, which is what we submitted. Then we're going to have an out file and an error file. This is what it's being output in standard output and in standard error. So the simulation is going to print some stuff while it's running. And this is captured so that we can look, and there is a bunch of information which you sometimes you want to look at. Well, often you want to look at, but I don't have time to discuss. So here, for instance, there's a bunch of stuff. Apparently the simulation crashed, so let's not look at this. But as we see, I know there's our theory, some information about the initial data, and so on. There's also, so this simulation requires 40 gigabytes. And that's why I couldn't run on my computer that's 12 gigabytes of RAM. So this is the out file. Then we have an error file, in which we have similar information. In this case, simulation failed. So we have some information about why the simulation failed. So sometimes you want to look at these files. And then we're going to have our folder static TOV that contains the actual outputs. So these are a bunch of files that contain the output that you chose you want to have in the par file. So if we once again look at the par file, there was here, there's a bunch of stuff that I say, okay, I want to output all of this. In this case, it's commented out, but here, there's some variables that say, okay, I want to output the minimum, maximum, average, normal, or do a norm utility of these ranges, and these are going to end up in my output. Now, in the old days, what you had to do is you had to manually work with all these files, which look like this. Like here we have a bunch of we have a mix of ASCII files, HDFI files, with a bunch of information like iteration time, value, and so on. The old days, you had to look at these files that I'm still mentioning, because if you do something weird, you probably still have to look at the files. But in the glorious new days in which I developed Qubit, you don't have to do any of these. Qubit is a package that I'm very proud of having developed to do post-processing of simulations of the Einstein Toolkit or Cactus codes. With Qubit, we can ignore all this structure that we have, the fact that we have all the simulation restarts. Everything is taken care for you. You don't have to worry about that. You can have a much higher point of view, which you just focus on the science and you ignore all the technical details. Now, Qubit is, which I'm going to discuss in my last 5 minutes, is a Python library that you have to install separately. So if we go back to our download, there's going to be instruction to download Qubit, which is just, if you're familiar with Python, it's just pip install Qubit. And once you install that, well, Qubit is a library, and Einstein Toolkit comes with a lot of examples on how to use Qubit immediately. So not only Qubit has a comprehensive documentation that you can find online, like Qubit. So this is the documentation for Qubit, so just the post-processing step, in which there's like first steps on how to install Qubit and so on, how to run some stuff. There's a lot of like tutorials that you can open and have a look at. So this is by far the best documented part of the Einstein Toolkit. So when it comes to post-processing, you're going to find a lot of information here. But you don't have to look at this if you want to do simple analysis, like making plots. So for instance, in this case, we have a simulation that is with some time series. For instance, I think we have, let's see what we have. Okay, for instance, if we want to plot the Hamiltonian constraint as a function of time in the simulation, we can use an example that comes with the Einstein Toolkit. So these examples live inside, oh, no. Here, was it here? Oops. So in Cactus, yes, I think. Let me see if it's true. Details, analysis, Qubit, examples. Okay. So here we have 2 folders. One is to make movies, one is to make plots. So we have a bunch of scripts here. For instance, let's assume that we want to plot the norm 2 of the Hamiltonian constraint. We can use the script plot time series. So what I'm going to do is I'm going to navigate to the folder where I had the data, which was in static TOV star. And I'm going to call my Cactus, repos, Qubit, examples, then plot time series. And let's see if it works. Okay, I have to ignore this just because I don't have Qubit on my computer. Okay. So if you don't know what a script does, you can just ask for help, or well, actually this was not help. This was help. So you can see all the options that you have in which for post-processing, which you don't have to do anything. You just have to read the options. So what it does, it plots a given time series as output of this calculation you're asking. So now the variable that I think we want to plot is, I think it's called h. And I think we want to plot the norm too. Let's see if this works. Okay. And now this is the Hamiltonian constraint, the norm 2 of the Hamiltonian constraint as a function of time. Now, what else do we have here that we can easily plot? Let's see if we have anything more interesting to plot. We have a bunch of maxima, like densities. I think we have 1D plots. Let's see if we can plot a 1D vars. We can plot, for instance, the pressure. Let's see how this works, if this works. And this, now, well, probably 1 log scale. So this is our pressure as a function of the x coordinate. So this is our star is near, and that's his atmosphere. So now I'm out of time, but I think this is the key elements that I'm going to summarize in the next 1 minute for basic usage of the Einstein Toolkit. Is, well, get components to get the Einstein Toolkit. Then foreign lists is the collection of modules that you want to download and you want to compile. So when you compile, you can choose a foreign list so that you get that. The configuration is a specific choice that you make in compiling the Einstein Toolkit with a specific foreign list or with a specific set of flags or whatever. Then you use SimFactory to compile and to submit runs. When you submit a run, you can keep on submitting runs if your simulation is very long and requires multiple checkpoints. Checkpoints are this collection of outputs for a specific time frame in a simulation, from 0 to 100, from 100 to 100, and so on. Then when you're done, or while you're running, you can use Scribit to inspect the output. Level 0, you can use all these scripts that, as we can see here, there's lots of scripts for lots of useful stuff, from plotting grid variables to plotting horizon stuff to plotting gravitational waves and computing gravitational waves. You can just use the scripts, or most likely at some point you're going to develop your own scripts. So you can always look at the examples and start from here to extend your own script. Now, most of these examples are overly complex because they are general. They're designed to work with any simulation that you run. But the core of this code is very few lines. So you can start from here and extend the code as you wish. And I'll go back to the documentation. Documentation for Qubit is you can just Google Qubit and you're going to find it. The documentation for the Einstein Toolkit is a little bit more sparse and it's not that great, honestly. There's a bunch of tutorials online, like videos on YouTube that you can find. I think there's a tutorial around here that very roughly, there's a tutorial here. Let's see. That you can follow to do what I was doing today. That is our single star simulation. And this tutorial is going to walk you, as you see, we have the sim set up to actually fill in the gaps that are left today, compiling and running codes. And at the end, we're going to have plot in some stuff with Qubit. So, and once again, my experience is that Einstein Toolkit is not easy. The best way is to ask for help. So if you're stuck, I'm always available to help you. There's a mailing list. Maybe you shouldn't expect an answer immediately, but please write to the user's mailing list. Someone will answer at some point. Or again, reach out to me. I will be happy to help. And I think this, again, is a good glimpse of the Einstein Toolkit. Once again, I know it doesn't make sense the first time. It's difficult. Don't worry. That's I wouldn't say how it's supposed to be, but it's a difficult piece of code. And any question?
I was wondering in the error path, like, I mean, that's probably when you compile it, it's an error, or when you run, like, I don't know, something that makes sense of error. But say it crashes just because, I don't know, you put whatever, the wrong binary conditions. Is there like any warning or something like when the code
Yes.
explodes?
Yes. Yes. So the question is, what happens when the code fails? Okay, now it can fail in multiple pieces. One, it can fail during the compilation step. In that case, you're going to get the error from this GCC or Gfortran that's going to tell you this variable is an initialized or whatever. If you just do the Einstein Toolkit as it is, if you're not modifying the Einstein Toolkit, you should not get those. Einstein Toolkit should compile unless you do something unorthodox with compilation flags or stuff like that. Typically, when you compile on a supercomputer, yes, at the beginning, you're going to get some compilation errors, like linking or stuff like that. And those, you get the errors from the compilation system, which is mostly GCC, this type of stuff. Now, when the simulation is running, then you can get very technical errors like the one I had here because I just downloaded some stuff from somewhere else. That is segmentation fault that has to do maybe with a bug in the code, which again might probably has to do with the fact that these files are just pulled from some place. It's not important. So you get, once again, you get the errors that are from your execution system. So this can be, again, you're as if you're running / whatever. So you get, you know, your segmentation fault, whatever. But Einstein Toolkit has its own systems to detect problems. For instance, here, suppose, so here I'm introducing dissipation. Suppose I introduce dissipation on a variable that doesn't exist. Einstein Toolkit is going to tell me, look, this variable doesn't exist. What are you doing here? So that might be an error or maybe a warning. If it's a warning, it's going to tell you, warning, this variable doesn't exist. If it's an error, it's going to tell you, error, this variable doesn't exist, and the simulation stops immediately. So there's, at the level of parameter file, there's a good system to catch if things are meaningful or not. That said, you can still very easily produce configurations that don't make sense and are going to produce errors that you don't understand. So sometimes you find errors, but it's not going to tell you, oh, look, this parameter is wrong. It's going to tell you impossible to communicate 5 points on the boundary. So in that case, it's a little bit more difficult. But most, again, as long as you don't modify the Einstein Toolkit, most often than not, you get some sort of explanation of what's going on that often you can figure out yourself. Not always, but.
Maybe I can ask some more questions. I do have some. So regarding Quibbit,
Yeah.
If I understand correctly, so it is to be installed because in those Python notebooks you showed load.
So yeah. So the question is, why does Quibbit have to be installed? So I can answer this question in 2 ways. The first is maybe you should ask why isn't get components installed in Quibbit, since get components does so much stuff. And the answer is Quibbit is an actual Python library, the same way it is NumPy, SciPy. So it lives on PyPy, which is a Python package index, and I want your Python installation on your computer to know about it. And get components cannot do that. Get component cannot mess around with your Python installation. Instead, we're using the default Python installation system that you have, which is probably pip. So that's why you have to install Quibbit. Now, Quibbit is a library, which means that when you install it through pip, you don't get anything. You just get this library in the same way you get NumPy, which is just this Python library that lives somewhere near your computer. But when you download the Einstein Toolkit, you get all these scripts with the Einstein Toolkit. If you run them, like now I'm going to. Okay, now if I open Python, if I try to import Quibbit, okay, I don't have Quibbit here. I was in a virtual environment. So now if I try running this, oh, actually, if I try running this, it's actually, I don't have Quibbit. So you need the library, and the Einstein Toolkit comes with all these examples for you that you can immediately run. Now, what I always do is, I don't like this. I don't like this super long stuff. So I define a variable in my shell called path. Now, if you're familiar with this task, it tells me, oh. So this is a collection of places where my shell is going to look for executables. And one is my Quibbit folder, so that I can always run my codes just doing what I'm serious. I don't have to provide any long path. It doesn't matter where I am in my system. I will always do it in this way. And so I highly recommend doing the same. And maybe I can use another minute to tell you about making movies, because Quibbit, I developed another package to make movies. It's called Motion Picture, and it's tightly integrated with Quibbit. And the interface with this MOPI, which you provide, once again, a file that lives in the Quibbit examples, so you get it when you install the Einstein Toolkit. And with this, you can make movies. Like I had a movie, let me see, I made yesterday. Like here, I have So this is a XY slice of the Hamiltonian constraint for a simulation that someone is running. And with this, you don't have to write any code. You can make movies like this immediately from your data. And once again, if you install Qubit, you get everything else for free.
Can I ask
Yeah.
another one? So for those, so this, let's say, pictures and movies these are supposed to be run. Is this some sort of like interactive notebook or something like this as well?
Yes, yes, yes. So the way Qubit is a library is because I don't want to impose workflow on anyone. I don't use notebooks. I use scripts because I can reuse them more easily and I can distribute it more easily. But what you can do is what I did in the documentation as an example is, so if you look at the tutorials, like read data. So this is a Jupyter notebook in which I import Qubit, and you can do this. If you like notebooks, this is exactly your plots and everything. The difference is that here you have to write the entire of the code yourself. So you have to understand how Qubit works. If you use the scripts I gave you, that's a very easy way to get something done without having too much understanding of what's going on. But eventually, I hope that people that get more knowledgeable with Qubit and are going to have their own analysis this way, because my scripts can do a lot, but they cannot do everything you want to do. So I think eventually you're going to go this direction. I mean, everyone is going to go this direction. I personally don't write notebooks, I write scripts, but you can just write scripts. And I am very proud of Qubit. The documentation is super thorough, and you can get a lot of information. For instance, here I explain every single example, or explain. Here you get all the examples with the code. You get some basic one-liner explanation of what the examples do. And if you're working with Qubit, you get all the APIs here, all the functions that are available, all the various expected arguments and types. So I hope that with the examples, and tutorials, and the documentation, you can do a lot of stuff. Like for instance, here we have Qubit already knows about a bunch of detectors. If you ever have to do something with detectors.
Can I ask something?
Yeah.
So when you were creating the plots or the video from the script, in which part of the command did you specify which file you wanted to use?
Which value?
Which file? Which
Yes.
file
Yeah, that's a very good question.
Is it already in the script, or did you?
Yes. So the most of what Qubit does. So the question is, where do I specify what file to use? Most of what Qubit does is to answer the question for you. So Qubit is going to look at all the files that you have. It's going to inspect them, and it's going to understand what you have in the files. So Qubit will know what files are needed depending on what you ask. So in this case, with this MOPI, what I wanted is I wanted to plot the variable zeta. And Qubit will find what files contain zeta. And that's why you don't have to worry about the fact that you have output 0, 0, 0, 0, 0, 1, 0, 0, 0, 2. Qubit will find the files for you, so you don't have to. And you can flip this around in the sense that now let me go back to. Now I think I have described. Yeah. So I have a Qubit script that tells you what you have in the simulation. So everything that is here is what Qubit finds in your simulation. So for instance, Qubit finds that you have 1D grid data for all these variables, and you have time series and have all this time levels, blah 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 blah. So this is one of the critical points of Qubit, is to take care of as much as possible so you don't have to. And this also allows Qubit to be very flexible. Like here, I have output 0, 0, but I could have whatever. Qubit is going to automatically handle whatever directory structure you have. It's going to look at the files. It's going to open the files and understand what's inside.
So So, and how is using Qubit compared to, for instance, physics?
Yes. So the question is how to compare Qubit, how do Qubit and Visit compare? So as part of the Einstein Toolkit project, there's also a component in Visit that allows Visit to open these files, open files from Cactus easily. Now, Visit is a massive package for visualization, most typically 3D visualization. Visit is a complex piece of code. You know, I assume most of you know something of Python. Visit, you have to learn everything from scratch. It's not very intuitive. You cannot easily have the script in which you can just make a plot. Every time you have to open the file, find your iteration, choose your bounds, all this stuff. So Visit is more powerful. It's much faster, much faster for 3D files than Python. But it's much harder, it's much less intuitive, and also it's mostly focused only on 3D files. You can maybe do 2D files, but it's nowhere near as good as this. And second, Qubit is not just visualization. With Qubit, you can do actual complex stuff. You can do post-processing. For instance, I wrote a ray tracing code that uses post-processed data from Einstein Toolkit using Qubit. Or I think I have another example here that I was working the other day. So what I'm doing here is I'm computing the determinant of the dead shape. I am computing the divergence of a field. Now, this is not super clean because I write in 2 minutes. But here I'm going beyond what you've done in my simulation. And you can probably do this with Visit, but here it's very clear what's going on. So Qubit is, I think it's much more powerful in terms of general exploration. But it's of course much weaker in 3D visualization. So if you want to make pretty plots, I've tried very hard to make pretty plots with Qubit. I mean, I can make something, but it's not the best, especially when you have like disks or stuff like that.
Mm-hmm.
Okay, if there are no more questions, if you want to try following the tutorial, following what I've done, please, feel free to do so, and I'm very happy to help you along. If you are already bored with Einstein Toolkit, you never want to look at it again, I understand it, and yeah. So once again, I renew my interest in talking to you guys. So please, I'm here to engage. So.
You know what? I was wondering one question. We worked with NERPy, but NERPy doesn't have checkpoints. So
well, so I don't know exactly. So NERPy does a lot of stuff. So NERPy, among the things that it does, it produces thorns. So I think if in the correct way, you should also work with checkpoints.
So in my experience, we are using NERPy just by itself.
Okay.
Okay. And as such, NERPy does not have API.
Yeah. Yeah.
So yeah. The next step would be to be able to create a folder.
Yeah.
And put into the
Yeah.
That's more work.
Yeah.
And also we're having trouble up here, so that's why we're thinking about moving from NERPy to the Einstein Toolkit with multi-processing.
Yeah.
But yeah, go also.
No. Yeah, I was wondering like how to integrate like the checkpointing as the Toolkit has to use it with NERPy or the other way around.
Yeah. So NERPy, what it does is it's a Python library to do high-level code generation from high-level expressions. And one of the features is also to produce thorns. So you can use NERPy to produce a thorn and use the Einstein Toolkit, but you can also just use NERPy to produce a C code that is standalone. In that case, you don't get any of the features of the Einstein Toolkit, and you have to implement the checkpointing system by yourself. So I guess that's what you're referring to. If all those features you gain all if you use the Einstein Toolkit infrastructure, or not if you stay in the standalone version.
I guess just out of curiosity, that are you aware of any thorns that are written in Julia?
Yeah, that's a good question. So there's no thorn that it's in Julia. Now I don't know what's the level of ABI compatibility. So it's everything here is at the end is compiled with C ABIs. So if Julia, so I know that people are some people are particularly interested in Julia, like a Perimeter Institute specifically. If you can compile somehow in a ABI compatible, C ABI compatible way Julia packages, then you can integrate them with the Einstein Toolkit infrastructure. At this point, the only thorns are in C, C++, and Fortran, or generated with Mathematica and Python 2C and C++ version. Yes. I also want to work with Julia, but probably it will be more like a side tool like Quibbit as opposed to something that works directly with Einstein Toolkit. Okay, thanks for your attention.
Thank you.